So Abhishek will tell us about matching vector codes.
Okay, so today we'll be looking at lower bounds on matching vector codes, which is a special family of locally decodable codes, and this is joint with Jadvir and Shaharlovet. Okay, so the plan of the talk is first I'll introduce what a matching vector family is, which is the central combinatorial object involved in matching vector codes. Then I'll show the link between matching vector families and how they give you good locally decodable codes, and then we'll come to the proofs. Okay, so what is a matching vector family? So take two subsets U and V in Gm to the n of the same size. So let U V be subsets in Gm to the n, and say U equals U1, U2, UK, and V equals V1, Vk. Now U and V will form a matching vector family if Ui inner product Vi is 0 and every other inner product is non-zero. So UV forms an MV family in CMN if, like I said, Ui inner product Vi is 0. So it's everything is mod M. So for all I, and Ui inner product Vj is not 0 whenever I is not equal to j. So that's the definition of matching vector family. Now this was studied earlier on in the context of set systems with restricted intersections, but that is a special case of this. As you can see, if you restrict your u's and v's to be in 0, 1 to the n, then they'll correspond to indicators for sets, and the inner product would be just the intersection. This is a slightly more general problem, and let's look at what bounds are known for this. Okay. Okay, so we'll look at M versus something called MV of M comma n, which is just the maximum possible size attained by any matching vector family in ZMN. So to be precise, it's exactly U, which is V, such that UV is an MV family in ZMN. The max of this. Okay, so if M is prime, almost tight upper and lower bounds are known. So if let's say M is large prime, then you have a construction which attains something like M by n to the n by 2, and this is an elementary construction, and this was proved in Dvir, Gopalan and Yakanin, but they had a 1 by m factor here, and that was removed recently by Yuan, Go and Khan. And you also have a matching upper bound which says that this is almost tight. So you have, this was proved by Dvir, Gopalan and Yakanin. This is only for prime M. Okay, so you can see if M is much larger than n, both of them are like similar, close to each other. Okay, if M is fixed, like a small prime, then you can't do much better than a polynomial set construction. So the lower bound is again an elementary construction which gives you something like this: n minus 1 choose m minus 1. This is polynomial in M, right, if M is fixed. And the upper bound is also something like this. So this follows from works of Babai Frankel, Frankel-Wilson, and similar techniques can be used even in the general case when they are not set systems. Okay, but for the case of composites, there is a huge gap. So okay, so if M is a large composite, then okay, then you still have this bound because this does not care about whether M is prime or composite. So you have, on the other hand, so it was conjectured in DGY that that this is almost tight. I mean, the proof techniques for the prime case do not carry forward for M, composite M, but it was conjectured that for large M this is almost tight. So in this work, first we'll prove this. This is indeed the case. So we'll prove something like M to the n by 2 plus some C log M, where C is a small constant. And you can see that as long as M is 2 to the small o of n, this is roughly like M to the n by 2. Okay. And okay, so this will be the first theorem. So we have, and we'll prove, we'll have two theorems, and both of them we'll prove just for M equals 6, just to give you a high level idea of the proof. So we'll prove something like 6 to the n by 2 here, and okay, so that makes this tight for large M. Okay, now if M is fixed and composite, and this is where it finds applications in good locally decodable codes, you have a construction by Goldman which gives you something like which is super polynomial. So you have where L is the number of distinct prime divisors of n. So where M equals P1 alpha 1 PL alpha L. So note that even if whenever, as soon as L becomes 2, you get a super polynomial construction. So one would ask, what do you get on the upper bound? Well, I mean, this bound still holds. You still have M to the n by 2 because M is a constant, so you can forget this log M factor. Okay, so we also show the following. So we show that this will be at most 2 to the Cn by log n, and this is under the polynomial Freeman-Ruja conjecture, which we'll come to shortly. So note that the in the exponent, instead of a half with n, now you have a 1 by log n factor with n. So for constant m, this is much better than this bound. So this will be our second theorem. So this will show MV of 6 comma n is something like Cn by log n.
Is there some consensus on where the truth lies for the composite, let's say for 6, what the MV6 n should be, where it is in this super polynomial?
Yeah, as you can see, the gap is still huge, but let's say you're able to prove a sub-exponential bound, even under PFR, then that would correspond. So if you're able to prove something like Ex of so yeah, no. So then this would give you a lower bound on the OR representation. The lower bound would be like log n to the 1 by epsilon, which would beat Barrington-Tardosh, because right now the lower bound is omega log n to the 1 by L, right?
So I'm confused by the theorem 1 and theorem 2. For the second one is n, or I mean,
In both cases,
It's for 6.
6 and n. So why? I mean, isn't
but the second is under the polynomial final ruler.
okay.
Yeah, under PFR. Yeah. So yeah, then you would, instead of so this is Barrington Tarder. So if you have something like this, you would get a log 1 by epsilon, which would be, so it depends on what your belief is in as far as the root log n and root n gap is concerned. So maybe a sub-exponential.
So this is just to say that, I don't know how many people know about this, and I don't know if you want to go in there, but matching vector families have applications to other related issues like
Yeah.
degree of.
Or and even Ramsey graphs. But now, okay, now we'll see how this relates to locally decodable codes, and after that we'll forget about codes, and then we'll come back to the proofs, because it's just a combinatorial object. And okay. Okay. So codes. So a code. Okay, good. This shouldn't take much time. So you have an alphabet sigma, and you take any subset in sigma to the n, and this would be a code. So let this be sigma to the n. So now you need many. You want to squeeze in as many code words as you can, so that you maintain the property that any two are sufficiently far apart. So why is that? I mean, what is the motivation behind this? Let's say you want to send a message a equals a1 dot dot ak, but instead of sending this, what you send is an encoding of this function. So this is some c in the code space, and what you receive, you assume that this channel is noisy, so you won't get the exact code word, but you'll receive something else in sigma to the n. And the hope is that the Hamming distance between y and c is small. So the Hamming distance is just the number of coordinates where they differ. So instead of receiving, let's say this, you get something here. So if each of them, the pairwise distance is high enough, then you can uniquely get back to the parent code word to which it belongs, and thus you can get back a. But oftentimes you need not, I mean, you may not want the entire message, right? You might just need a single coordinate, let's say ai. Then it doesn't make sense to look at all the capital N coordinates and then back calculate out and then come to a and then just output ai. Maybe you can just use the locality in the code word positions to just read a few locations and be able to comment about what ai is. So that's where a locally decodable code comes in. So okay. So yeah, so C is an R delta LDC. If there is an algorithm, if there is algorithm A such that for all I in K, this is going to be the index you need, and y in sigma to the n, and let's say y is close to some code word, the following two properties hold. One, you have that given oracle access to y, a on input I would give you ai with high probability. So by oracle access, I mean that a can just write down which coordinate it wants, and it will get exactly that coordinate from y. And it's an R query LDC. So now a makes at most R queries to y. And throughout we shall think of delta as a small constant. So the main interest in LDCs is to study how R behaves with the stretch, that is you would intuitively think that if R is small, you would need a lot of redundancy in your code word, which means that capital N has to be much bigger than K. So that is what people have studied, and let's quickly review what is known. So here we have R, and here we'll have N versus K. So for R equals 1, there are no LDCs known. So this is from Katz-Trevisan. For R equals 2, you know things, you know how it behaves very nicely. So you know that N is exp of theta k. That is, there is a simple construction which gives you an exponential stretch, which is the Hadamard code, and the lower bound was proved by Goldreich, Karloff, Schulman, Trevisan for the linear case, and for the general case by Kernedish and De Wolf. But for higher R, as you will see, there is a huge gap. So for here onwards, all you know is that. So on the lower bound side, you know that K is at least, the N is at least 1 plus this function. And if you look at it closely, you will see that for R equals 3 and 4, this gives you a quadratic lower bound. And for any other R, it's just slightly superlinear. But this was by Woodruff. Okay, but on the other side, so a very recent breakthrough result was that you can actually get sub-exponential sized codes. So you have okay, I'm hiding some. So as you can see, this is since it's small of log n, it's a sub-exponential term. And yeah, so this was given by this was first discovered by Sergei Yakanin, and he proved a sub-exponential bound under something called a Mercian prime conjecture. But then soon after, Efremenko removed any dependence on conjectures, and he slightly improved the bound, and then he got the sub-exponential bound without any assumption on conjectures. And now these are what are called as matching vector codes. And as the name suggests, matching vector families play a key role in the code construction, and we'll just see a quick construction of a matching vector code from matching vector families. So now what we are showing is matching vector family implies matching vector code. Okay. So let UV be a matching vector family in ZMN. And let M divide Q minus 1. You'll see why. Q is the FQ that we are going to work on. R is still R. Yeah. So let K now we. Okay, so we'll now come up with an encoding function that takes a message in FQ to the K and spits a code word in FQ to the N, where N equals M to the N. Okay. So how does it go? So okay. So let's say you have A equals A1 through AK. Now E of A would be, it will be an evaluation of some function which is so AI. Okay. Yeah. And okay, before that, let omega be an mth root of unity in FQ, primitive. Okay. So okay, so function is summation ai ui x, and it will be evaluated at all m to the n locations. Okay, so this is your code word, and you can see that this belongs to fq to the m to the n, right? Okay, now let's say you want to get back aj. Okay, to decode aj. Okay, so what do? Let's say this is the received word y. We'll assume it's error free, because by union bound, since we'll make very few number of queries, you can ensure that all the locations are error free. So to decode aj, we'll query y at the following coordinates. So at x plus lvj, 0 less than l less than m minus 1. So we'll query it at this multiset. Okay. Right now, yeah, this is true for any x, but we'll choose x random. This will make that if error free, it's true for any x. Okay. So now we have queried y at these locations, and what we'll do is we'll simply add these coordinates up. So till now, yes, you can see that it's an m query process. Okay, so if you add up, all these coordinates, what do you get? You get ai 1 to k, l equals 0 to m minus 1, omega to the x plus right. So this is what you get. Oh, okay, okay. Thanks. Right. So now, as we shall observe, everything other than the term corresponding to aj will cancel off. So if I is not equal to j, then let's look at what this gives you. So okay, so what do you have? You have L going from 0 to m minus 1, and okay, you can take ui inner product x outside because it does not have any dependence on L. So what does this equal? So this is some number which is non-zero by the definition of a matching vector family, right? Because it's a cross term. So you have, so I'll replace this by some constant c, right? And what is this? Since omega is primitive, this is 0. Right? So the only thing that survives here is the term corresponding to aj. So you have aj, and then what do you have here? You have omega to the uj x, and this added m times. And you can show that m won't be divisible by the characteristic of the field by the fact that m divides q minus 1, and this is how you can recover aj by pulling these to the other side.
You know with j and
you know x, yeah, exactly. So the matching vector, so u and v was your matching vector family. So u was used only in the encoding, and in the decoding you used v to, yeah, okay. Okay, so how does this paradigm fit in? Well, what did we get? We got a code from k symbols to n symbols, right? So if you can prove an upper bound on k, where k is the size of the matching vector family, it means that it's automatically lower bound on the stretch. So something like, so let's say theorem 1. Okay, so theorem 1 here. So if you prove k is less than m to the n by 2, it means that n is at least k squared. Similarly, if you plug in the next, so under PFR, so what do you have? You have k less than 2 to the Cn by log n. This would imply n is at least k to the log k to the log k. So a super polynomial stretch. Okay, so now that we have seen what the motivation is, let's come back to the theorems and prove both of them. Okay.
There's no suggestion of trying. I mean, in many codes, sometimes you can look at evaluations not at all points in the field, but in some.
Yeah, so you can do some ad hoc tricks if the output UI inner product Vj follows some niceness property. But for example, claims construction, he got 3 query LDCs, but he did a computer search to see that for m equals 511, you do not need to do 511 queries, you can just do 3 queries. But barring all those ad hoc tricks, if you just follow this general construction, this would give you, so you can see that m is like an upper bound of the number of queries, right? So if m is
fixed. Not asking about whether m is an upper bound of the number of queries, but rather to get a better rate than what this gives. In some codes, you can evaluate the function, so the vector you write down.
Okay.
Evaluating in all points in this FM.
Okay.
In some cases, you can.
Right.
In various other cases, you can say by
evaluating only
on a subset.
Right. Like you do 0, 1 to the n for hard.
Do 0, 1 to the n. You
FQ.
can have, I don't know, some basic sets. I don't know.
Okay. Yeah.
So there is no such trick for locally decodable codes.
No, I mean almost, yeah. I mean the very first construction of Sergey was a bit different, but other than that, they all evaluate. I mean the evaluation is at all m to the n locations, and the only tricks that are used is to, instead of querying it at all the m locations, you maybe query it at 3 locations or 4 locations.
There is always a possibility of choosing m to be super. As long as m is constant, just one constant to different constant. Potentially you could use m which is as large as n and still somehow get only 3 constants.
Yeah. Right. Then you can bypass this. But again, you can't bypass a quadratic bound because that is true even if m is 2 to the small o of n. Right. But yeah, you can bypass this bound. All right, so let's prove theorem 1.
You're going to say anything about this construction of the.
I'll do a quick construction at the end if I get the time. Yeah. Okay. So what are we trying to prove? We are trying to prove that you have an upper bound of 6 to the n by 2 for m equals 6. Okay, so let's look at the intuition first. So the intuition comes from 2 source extractors. So let's say u and v were subsets in Z2 to the n. Okay. Now you know that if the size of u times size of v is large enough, then the inner product small u small v, where u is drawn from capital U and v is drawn from capital V, would be close to uniform. On the other hand, if U and V were matching vector families, then by the very definition, U inner product V would be 0 with very, very low probability, right? For any U, you would have to pick exactly the matching V. So naturally, this is far from uniform. So if U times V is large enough, you get a contradiction. Which upper bounds? So the intuition is that if U V is large enough, so we are looking at Z2 to the n, then the distribution U inner product V is close to uniform. But if U and V were matching vector families, then U inner product V would have 0 with very, very low probability. Then it's 1 by k, which is much, much less than 1 by 2, which immediately means that k squared is at most 2 to the n, which means k is at most 2 to the n by 2. Now this proof technique would go through as long as m is prime, but the moment it's composite, things go bad. Okay, so let's say m equals 6, and you just take u equals v equals 0 to 4 to the n. So now note that the inner product uv would never take the value 1, 3 or 5. So it's at least half away from the uniform distribution. On the other hand, if you look at uv, it's as high as 9 to the n, which is much, much more than 6 to the n, right? So you have to do something more. In fact, this example is going to guide us in the proof. We'll first observe that if the distribution u inner product v is far from uniform, then in fact this is the only obstruction you get. That is, there is some factor of 6 modulo which a lot of u or v would collide. For example, here everything collides mod 2, right? And that would be enough to give, that should drive the induction forward, as we shall see. Okay, so now we'll start the proof.
The size of this obstruction has to do with the factorization of the composite.
Yeah, exactly. You'll get like a, so if the factor is s, you would get a minus s to the n by 2 fraction. Okay, so we'll need the following claim, which we'll use again later, so I'll write it over here. Okay, so let D be a distribution over U Zm. Now, if the distribution is far from uniform, so this is the statistical distance between the two distributions. If this is high, then some character would be biased. So
You're doing a single bit, right? The distributions are not just a single
UM.
not a value.
Yeah. And
The output of the inner product.
exactly, that is what my distribution would be. So yeah, where omega is some mth root of unity, omega non-trivial. Note that omega need not be primitive, which is what is going to give us the obstruction. Okay. So let's see. So we'll use
So what if omega is like a second root of unity and we take
Yeah, so then you'll get a lot of collision, and that would give you a contradiction. So we'll just prove soon that matching vector codes cannot have such high amount of collision.
But don't you get that 0 in plane A? Or a third root of it is
Then
0.
there exists something.
Oh,
I see.
okay, yeah. Yeah, okay, thanks. Should I prove this?
Yeah.
Okay.
Okay.
Inshallah.
Better over composite.
Yeah.
It's a
Very dependent.
okay. Okay, so what do you have? You have 2 epsilon is okay. So I'm calling d of x to be the probability mass on x. So you have x in Zm, right? This is the statistical distance. Now, okay, now you'll do a Cauchy-Schwarz, and you get root m times sum of squares. Okay. Now you'll get a 1 by m here, so that you could use Parseval at the next step. And so now what is this? This is exactly equal to, well, it's equal to d hat j minus u hat j squared. But d hat of 0 equals to u hat of 0 because it's a probability distribution. And everywhere else u hat of j is 0, right, because it's a constant function. So basically all you have is d hat j squared, right? Now, okay, now this will be less than m to the 3 by 2 d hat j max, right? Now if you look at d hat j, if you write on the expansion of d hat, what is it equal to? It's exactly equal to 1 by m summation x dx omega to the minus jx, where omega is some primitive mth root. Now if you bring the m on this side, this is exactly equal to expectation of omega to the minus jx. So you get this particular j out, and that's why I didn't write omega to the j, but I just wrote some omega where omega need not be primitive. No, it will still be there. Eventually you'll get 2 epsilon by root m here.
Oh, I see. M is a constant.
M is a constant. Okay. Right. So now we'll apply claim A with, we'll note that the following distribution U inner product V is far from uniform, because why? Because probability that UV is 0 is very, very small. Because this is like 1 by k, which is much less than 1 by 6. So we are assuming, for the sake of contradiction, that this is much greater than 6 to the n by 2, and we'll get a contradiction. So you agree that this distribution is far from uniform, so you can apply this.
So, because it's a matching vector code, definitely this distribution is far from yours.
Yeah, so let uv equal to k. Right? Okay, so what do you get from here? You get, by claim A, you get expectation omega uv. This is large, right? Now observe that the only values of uv that matter are what it takes modulo s, where s is the order of omega, right? So let s be order of omega. So in this case, s can be either 2, 3, or 6, right? Okay. So naturally, the next step would be to look at everything modulo s. And now the only thing that changes is that now you'll get, it's no longer a uniform distribution over elements of a set, but you'll have some distribution corresponding to the.
What collapses because you're taking a mod s. Okay.
So define what the natural. Let's define two distribution mu1, mu2 from zs to the n to 0, 1 as follows. So mu1 of x would be exactly all those u in u such that u equals x mod s. X is in Cs to the n, right? And similarly, mu2 of y is all those v in v such that v is y mod s, right? Now we'll rewrite the entire thing in terms of. Okay. So let's rewrite that the conclusion of claim A again in terms of these distributions. So you have x in mu1, y drawn from mu2, omega to the xy is large, right? Now this, note that this is primitive now in ZS, right? So this is important. Okay, from here, so if you have 1, so 1 implies that collision probability mu1 times collision probability of mu2 is large, and this is where the factor of m comes in. Okay, so to see a quick proof. Okay, so we have this, right? So what do you have? We have epsilon prime, which is so x mu1 x, y mu2 y, omega to the xy. Right, this is just rewriting this. Now, okay, I'll push the absolute value inside by triangle inequality, and now I'll do a Cauchy-Schwarz, and here I'll get collision probability mu1, and what do I get here? I get summation over x, and then y mu2 y. Right. So now the usual trick. I'll write this square as two independent summations. So I'll have y prime, right? And now let's interchange summations. Oh, sorry. Thanks. Okay. So now if we interchange summations, let me just do that here. Now if y is not equal to y prime, this would evaluate to 0, and if y equals y prime, you would just have mu 2 y squared, the sum of that, and this gives you, so you still have Cp mu 1 from there, and you have Cp mu 2 added s to the n times, and this proves the claim. It was important, but otherwise this won't cancel off, right? Because if y minus y prime were equal to, let's say, some bit was equal to 2 and this was, let's say, minus 1. Okay, so let's say this were 2 and this were minus 1, then it will automatically give you 1 and there is no cancellation. So this was important here. Thanks. Okay.
So that sum over x you extended to all.
No, here there is no need because x is es to the n. I don't want to erase that. Okay. Okay. So now we have that at least one of the collision probabilities has to be high enough, and this is how we will get our collision. So let's say Cp mu 1 is large. Cp mu 1 is large.
So for uniform distribution, yes, we expect collision probability of 1 over S.
Yeah, 1 over the, yeah. Here we'll, since epsilon prime is a constant, we'll write it as 1. Okay, so it won't matter. What you should keep in mind is that this factor of s to the n by 2 is what is going to help you. So if Cp of mu 1 is large, then since this is the L2 norm squared and the L1 norm is bounded, it means that there is some large enough block. So to formalize that, you have mu 1 x times max mu 1 x, right? You can always do this, and this is roughly 1 over s to the n by 2, and since it's a probability distribution, this is 1. So you have some x star at which mu 1 of x star is large, right? So okay, so where was mu 1 defined? Okay, so now if you look at the definition of mu 1, it means that if I take all the elements of u which collide to x star, then I'm getting a 6 over s whole to the n by 2 sized subset, right? Because u is like 6 to the n by 2, and you lose out a s to the n by 2 factor. So implies that if I construct u prime to be all those u such that u equals x star mod s, and v prime I'll take exactly matching with u prime. So v prime is all those vj in v such that uj was picked in u prime. Okay, so that the matching property is still maintained. So now, okay.
Just in the happy case if S was exactly 6.
We will do
Okay,
yeah. So what do we have from 3? 3 implies that this is much bigger than 6 by s to the n by 2, right? I just rewrote. Yeah. Okay, so at this point we'll introduce something called, so that we'll introduce the inner product matrix corresponding to u and v. So this matrix P, so think of all the elements of u here and v here. So the ijth entry is simply ui inner product vj. Okay, So now you can observe that on the diagonal you will have all zeros, and all the off diagonal terms will be non-zero. And now we have some u prime, a subset of u. So without loss of generality, let's say the first few rows, and we are taking the matching elements from V. So this is u prime, this is V prime. Okay. So observe that P u prime cross V prime is the all zero matrix mod S for any S in 2, 3 or 6. Why is that? So we know that these are 0 mod 6, so it's 0 mod any factor of S. Also every element in u prime is the same mod S, right? So these rows are the same, exactly the same mod S. So if you look at its row of inner product, they'll be the same. So if you have a 0 here, a 0 here, you'll have a 0 here, 0 here, and so on. So everything is 0 mod S. Okay, good. So if yeah, I'll do that simple case now. I won't do that. Yeah, sure. No, it will be 0 mod S though. It will always be 0 mod S. No, but if it's the same vector mod S, and if all these are 0, then it's 0 mod S. We'll use that in the next step. Okay, so now we have established that this is 0 mod S, right? So now a simple case analysis. So the happy case, as you say, S equals 6. Okay, so if S equals 6, since it's a matching vector matrix, you cannot have 0 on the off diagonal. So even if you get u prime v prime of size exceeding 1, you have a contradiction. But what do you have here? You have something which is much greater than 1. 6 by 6 whole to the n by 2. Right? So it's much greater than 1. Right?
It's greater than 1.
No, there's epsilon, right? So you need much more.
Yeah. There's a yeah. Okay, so done. Okay, now if S equals 2, S equals 3 is similar. So say S equals 2. So then you can observe the following. In this case prime, but yeah. But the claim you'll see is more general. So u prime v prime is a matching vector family in Z3n, right? Why is that? So you want to show that everything on the diagonal is 0 mod 3, which is obviously true because it's 0 mod 6, and the off diagonal terms will be 0 mod 3 because they are 0 mod 2. They'll be non-zero mod 3 because they are 0 mod 2, because if it were both 0 mod 2 and 0 mod 3, it would have been 0 mod 6, which is a contradiction. So now if the bound here exceeds what is allowed maximum for a prime case, then you get a contradiction. So what do you have? You have a matching vector family of size much greater than 3 to the n by 2, but by the prime bounds you know that it can be at most 3 to the n by 2. So you have a contradiction. So you have k prime much greater than 3 to the n by 2, which is not possible for a matching vector family n. Okay, so
And otherwise you reduce to smaller n.
yeah, so let's see. Okay, let's call this claim 2. No, not this. Okay, so as long as m is a product of distinct primes, you know that whenever you get something which is all 0 mod S, you can get an MV family in m by S, because S and m by S would be coprime. However, claim 2 would be false if m is, let's say, p squared q squared, right? Why is that? So say m equals p squared q squared, and the S you got was like p squared q. So now you have something here which is all 0 mod p squared q. Then it will be all 0 mod q as well, right? because Q divides it. So it cannot be a matching vector mod Q. Right. So you can't do Chinese remaindering in such cases. But you can do similar kind of stuff and get around this problem and make it work even for product of repeated primes.
So even in the p square case, can you say?
The new no. Okay. So proof idea is that instead of reducing to smaller factor mod n, what you do is you look at uv, which you start with, assume it's large enough. Let's say it's much greater than m to the n by 2, and at each step you take a subset u prime v prime, so that so you looked at mod r1 and v looked at mod r2 are the same vector. So the base case for this would be r1 equals r2 equals 1, right, because everything is the same mod 1. Now after each step you somehow get to another subset, so that modulo r1 u is a constant, right. So this r1 and r2 will depend on what you're getting here. I mean, you just have the product of collision probabilities high, so you'll get a collision in one of them. Each time you ensure that one of them grows and you don't lose out much in the size, and ultimately you'll end up with some subset uv such that u is fixed mod s and v is fixed mod m by s, and then you can show that such a matching vector cannot exceed anything super polynomial.
So in the Z4 case, say, the R1 and R2 will both be 2.
It can be 1, 4, it can be 2, 2. All you'll be guaranteed at the end is that the product is m, and that would be enough to get a contradiction, because you can show that if all elements collide mod r1 in u and something collides mod r2 in v, then you can show that the inner product uv has to be constant mod r1 r2 after some pruning, and this cannot be allowed if the size that you end up with is more than 1. So this inner product being all 0 is mod m, it's not mod s, so you can't allow anything more than 1. So yeah, I don't want to do that. The rough idea is again, high bias implies good collision in buckets.
But this is a number theoretic thing. I mean, just say that if you have a set of vectors which are constant, let's say they are 0 mod r1, and another set which are
Then the uv would be constant mod r1 r2 up
S and m over s, then the inner product is
fixed
mod m,
mod m,
the product.
mod their
So
product.
they are-
It won't be
Well,
fixed, you'll have to
whether
prune.
product is m, doesn't matter whether they share primes or not.
Sure. The only thing is that you'll have to prune a 1 by m squared fraction to make it, because it's like everything here can be written as r1 x plus something, and everything here is like r2 x plus something. And if you do the cross product, r1 r2 would be 0 mod r1 r2, and the cross terms only have one thing that is varying, so you can always fix the most popular one. And in case of matching vectors, if the inner products are all constant, it has to be 0, right, because the diagonal is 0.
So this S was the order of
Omega, yeah.
But you picked omega sort of on the average, so can't you?
No, S can be anything, yeah. So whichever, where is
But
that?
when you select omega,
Yeah.
One bias, maybe that all of them are 0 mod. Possible that the omega is fixed for you. But it's tight, so this argument is really tight. So we have this one. I mean, the prime case is tight.
Yeah, just take, try to avoid, so you take p to the n by 2 here and keep the other coordinate 0, and the other case fill up those coordinates. Okay, so I think before starting theorem 2, if you want, we can take a 5-minute break. Okay, let's come to the second theorem now. So we are trying to prove MV of 6 comma n is at most true to the Cn by log n under PFR. Okay, so it will now make sense to talk about the rank of the inner product matrix that we were talking about. So let's since we are working over ZM now, it's so many zero divisors, so I'll make it very precise. So rank of a matrix P over ZM is it's a minimum R, so that you can write P as a product of a K cross R matrix and an R cross K matrix.
The sum of rank 1 matrix.
Yeah, but we'll use this.
Yeah, it's okay, but it's the same.
It's okay. Yeah. Stat P. All right. So now that we have this, okay, another thing that we'll need is, okay, let us again come back to the inner product matrix more formally. Okay, so given UV, or let's say, okay, MV matrix P, which is K cross K over ZM, is any matrix that has 0 on the diagonal and non-zero everywhere. Now let's say this matrix had rank R, then by the above definition, you can get a corresponding matching vector family in ZM to the R, right? So if rank of P is R, it means that there exists some A and B, or U and V, okay, A and B, equal to P. Right? So now this is of R length. Now if you look at any ith row and jth column here, it will give you the ijth entry here, and if you call the rows of this as your capital U and the columns of this as capital V, you have a matching vector family in ZM to the R. Okay, on the other hand, if you have a matching vector family, so this is 1. So if U and V is MV in ZM to the N, then the inner product matrix that it gives is of rank at most n, right? Then P defined by UV has rank at most n. Why is that? So P UV has one candidate decomposition as U times V, which is like, so P is equal to this is one decomposition of P, but the definition of rank says the minimum such, so the rank is at most n. So you can think of n as in some sense the rank of the corresponding inner product matrix.
Why in some sense without also general?
Without, yeah, because we will be,
Otherwise you can make it smaller, right?
it will be only to your advantage if it's smaller.
So we can assume n is the rank.
Okay, yeah. Okay, and another, okay, a key ingredient we'll use is the submatrix lemma. So this basically tells that if you look at a matrix and let's say we are looking at m equals 2, if the distribution of zeros and ones are not close to uniform, then you can find a large enough submatrix which is all 0 or all 1. That's the rough idea. Okay, so submatrix lemma, this was first proved in by Ben Sesson, Lovett, Zevi over Z2. And it extends easily over any prime, but for composites you have to do some. So firstly we generalize this to any ZM with the same bounds, and it's more of a technical contribution rather than a conceptual contribution, so I won't go into this. The ideas are still the same. So what does it say? Yeah. Okay, so assume PFR. And let A, B be two subsets in ZM to the n. Now if expectation omega AB is large, then this implies that you can find a large enough A prime from A and a large enough B prime in B, so that the inner product AB is constant. So then there exists A prime in A, B prime in B, such that firstly they are large enough. So and similarly B. And the inner product A prime B prime is fixed.
I mean, this is like a monochromatic rectangle.
It's a mono. Okay, it's a monochromatic. Yeah. For all A prime in A prime, B prime in B prime.
And what will the large mean? Just larger than some.
Okay, so large is, in fact, this works for any 2 to the square root n. I just need constant.
Unit constant.
1 by n.
Yeah, so I mean this follows from PFR, but and maybe there's even stronger result, right? So it's so this may be true independently of PFR.
This may be true independent.
And maybe easier to prove.
Maybe, yeah.
Formally, it's always.
Wait, but so right now, I mean, we don't have better. I mean, we have an improvement to log rank under PFR, and we don't have an improvement to log rank without PFR. So, I mean, would you think you can? I mean, prove
I mean, it's
this
not
without
easy. Yeah.
PFR? I mean, it seems.
What's the best you can hope for in this one?
I think here you can hope for 2 to the minus square root n.
Even for when the large and constant of the
Yeah, even when
Yeah, this does not
this is
matter
even
actually.
the original papers of everyone.
But there you get a delta n here.
No, that
But here it's 2 to the minus n.
this technique is
Yeah, this. Yeah, this. Yeah.
Oh, this technique, but what
Yeah,
about?
what's the best you can hope
no,
for?
it is just not true. We have there instead of 1 or that 0.99 and since A prime and of size 2 to the minus root n times n. So you won't find large monochromatic cells just for this assumption.
But it would be really interesting to prove anything like that without this.
In some sense, we know it's semi-equivalent, but it's equivalent to a restricted version of PFR. So assume you're doubling some large and it's equivalent. Like that is
It's not a constant.
no, the approximate duality, if your doubling is not constant or something like the epsilon n, then this is equivalent.
And without the PFR, what's the best?
Here then you will need something like 1 minus. The bias requirement is like 1 minus epsilon. Very close to 1.
And then you're going to do to the minus, I don't know, to the minus n over log n.
Here, I don't.
One thing which is not unconditionally is that you have 1 minus epsilon and epsilon
Here
squared,
it's 1 minus
which is
epsilon.
which is minus delta n. Delta,
I don't know about n by log n. But yeah. And omega here is primitive. So okay, so I'll just state what PFR states. So this is stated more generally, but we'll just need the ZM version. So let A be subset in ZM to the n, and let's say A minus A does not grow too much. Okay. Then it gives you a handle on how close A is to to an approximate subgroup. So it says that then there exists an A prime in A which is large enough C is a universal constant such that the span of A prime is small.
So, in when you start with the matching vector family, this expectation is very close to 1.
No, it's 1 by square root m. It's even for 6 it's like 0.6 or 0.7, and that idea fails. It doesn't work. Yeah. Even for mod 6 it's 1 by, so you get 2 epsilon by square root m.
the other claim, you know, you have this uniform distribution of orders and non-zero. Yeah. So it doesn't have any very large Floyd coefficients. The coefficients are not zero, though. Yeah, model, let's see.
So it's okay. So the converse is simple to see. It says it means that if you have a set that is close to its span, then it cannot double too much. But on the other hand, the harder direction is, okay, can you characterize approximate subgroups just by looking at how they double? So if you are willing to have a polynomial loss and go to some other A prime, then C is a universal constant.
Universal.
So it's
Depends on m. Right? So it's universal, but depends on m.
oh yeah.
Okay, again, in general, it's not dependent on m.
For any m, yeah, there is some Cm. That's what it says.
I guess this was never studied by anybody, right, for composites. I just
No, it's. I mean, it's generally over abelian groups. So all the results.
it was stated from the start for opinion groups, I thought.
It was stated for any low torsion group. Yeah, for any abelian group with low torsion. 93 when Ruja Freeman theorem proved. But we'll just use the ZM version. Yeah.
How does this relate to, I mean, PFR or Z2 to the N and Z3 to the N? Does it imply this?
No, I mean not trivially.
And there's no PFR or Z to the N.
No, then you'll have gaps, right?
Oh, okay.
You'll have GAPs.
Over 6 implies 2
Oh, I said.
Yeah, because they also live inside Z2 to the n, but it's better inside Z6 to the n.
Okay. So yeah, from higher you can.
And you
But
think
only to.
C should depend on M?
We,
Or M because changing.
it depends on the order of the element.
Okay.
Yeah. All right. So recently Sanders proved a quasi-polynomial version where he had k to the log cube k instead of k to the c, but that doesn't work in. That doesn't help you.
And his proof works
Or ZM.
for ZM.
Okay, so let's. Okay, so what is the high level idea? So you want to show that MV of 6 comma n is at most something. So this is k cross k, and its rank is n. You want to show that k is at most some function of the rank, which means that you're trying to lower bound the rank of this matrix. So how would you go about doing it? Let's say you come up with some iterative trick where each step you get a submatrix where the rank goes down by 2, but the submatrix is still large enough. Okay, so you get submatrix rank goes down by a factor of 2. And at the same time, the submatrix isn't too small. Then after log n steps, you would have a rank 1 matrix, and yet you would have a huge matrix left, and this would be a contradiction. If the rank was low enough, if you assume the rank was low, then this would give you a contradiction, right? So this is a very rough.
But if the submatrix is still the matching vector,
It is a, yeah, there are no repetition columns. Yeah, the submatrix will be symmetric, so each time you will get something like this. Yeah, I'll make that precise in the next.
So, I mean, is this similar to like, there's this Aho, Ullman, Yanakakis, way of sort of upper bounding the communication complexity by sort of.
I've seen this kind of thing where you have a monochromatic. Yeah, I think it will become more familiar when I write the next. Okay. Okay, so let's say you have a matching vector matrix P, right? So this is U, V, and this is P of U, V. Right? So now we know that this distribution is still biased because it's corresponding, because the number of zeros is very, very small. So we'll use claim A to observe that. Okay, which means expectation omega to the UV is large, right? And right now, let's assume omega is primitive. Okay, so what do you have? You have expectation UV is large, right? Now, immediately you see you can use the submatrix lemma, and since that works only for primitive omega, by the way. So if the bias is large enough, then you get a large enough submatrix which is monochromatic mod M, right?
Yeah, it's not a symmetric one.
It's anywhere, it can be anywhere. Okay. And so, okay, but you want to reduce somehow to the case where you get a matrix just like a matching vector matrix. So what you'll do is, let's say this is R1, R2, you'll complete this and construct this smaller submatrix. Its rank can only go down. So you have C here, this is R1, R1. So these are again matching vector matrices, right? And both of them are large enough by submatrix lemma. So you have, okay. Okay, now let's make this 0. Okay, so we'll add a rank 1 matrix to this. So we'll add the following matrix and make this 0. Okay, so the rank of this is still less than or equal to n. Okay, so here now you can see what we are going to do. We know that.
So you're going to recurse on one of the two
So let's call this A, let's call this B. Now you know that R of A plus R of B would be, okay, so I added a rank 1 matrix, so I'll have n plus 1 here. This is at most n plus 1 by 2. R of A plus R of B is at most n plus 1, which means that at least one of them should have low rank. Okay, so let's say R of A has low rank. Well, okay, so why is this good for us? Because now you'll recurse, as you observed, on A, and this time the rank is n by 2. So if you plug in the submatrix lemma, the submatrix, the n here is actually the rank of the matrix. So this time, so initially if you had P0, now P1 would be at least 2 to the minus Cn by log n P0. Similarly, P2 would be, now it's a rank n by 2 matrix, so P2 would be Cn by log n minus Cn by 2 by log n by 2 P0, and so on. If you continue up till log n steps, you get something like 2 to the minus C summation n by 2 to the I log n by 2 to the I. And this roughly behaves like 2 to the minus Cn by log n for a larger C. Now if P0 was large enough, much larger than this, then you have a super polynomial size matrix, but its rank is 1. But since any matching vector matrix has zeros like this, then if it's rank 1, then it has to be all 0, right? Even if you put any non-zero element here, it will give you an extra element. It will increase your span. So this is the rough intuition, and now we'll see two glaring errors in this proof and some minor issues that we won't tackle. For example, the submatrix may overlap with the diagonal, and then you can't do this. So then you can get a win-win situation, case-based analysis. But there are minor issues. But two major things are the following.
The omega, no?
Yeah, that's one. Good.
Omega and the rank.
2, yeah. Okay. So problem 1 is omega need not be primitive. And then you can't use the submatrix lemma there. And problem 2 is so this claim is not true. I mean, if you have a matrix like this, then rank of A plus rank of B is not less than equal to rank of. So very disturbing. So just look at this matrix. Let's say M equals, so rank of A plus rank of B is not rank of A0 B. Okay, just take M equals 6 and look at the matrix 4 3 0 0. It looks like a rank 2 matrix, right? But here's a rank 1 decomposition, right? So which means that rank of 4 plus rank of 3 is not less than. Right? So that step fails. So first we'll fix problem 2 and then we'll come to problem 1. Okay. Okay, so we define another rank which satisfies this, but now the submatrix lemma uses the rank notion defined there. The submatrix lemma uses exactly this notion of rank. So then we'll show an equivalence between the two definitions of rank. So let P be K cross K matrix over Zm. Now define the column rank of P. We shall write CR of P later. This is equal to, so look at the span of all the columns of P and the size of that log base m. Okay. So this, so you have P, you look at the columns, take the span of the subgroup, generate additively by the columns, and take log base m.
This need not be an integer.
Right. So yeah. So now, firstly, you can, this holds with R replaced by CR. So let P be this. Okay, then you have CR of A plus CR of B is less than equal to CR of P. I mean, you can prove this by looking at column span A cross column span B and defining an injective map to column span P. But just to play around with it, let's see what we get if we exactly use this matrix. So what is column rank of 4, which is A here? So it's exactly log base 6. Okay. So you'll have 3 elements, right? 4, 2, and 0. Similarly, column rank of 3 is log 2 base 6. So as you observed, it's not an integer. But what is column rank of P? So it's all those A comma B where A can be 0, 2, or 4 and B can be 0, 3. So you have log 6 base 6. So column rank holds, right? Okay, now we fixed problem 2, but what does it do to the submatrix lemma? The submatrix lemma has rank here. Okay, the large enough submatrix that you get, so that is in terms of the rank. So the next step you can prove is that, you can prove that the column rank is nicely sandwiched between R by log m and R. Okay, so instead of, this tells you that you don't lose out much if you use column rank instead of rank. You just lose out a log 6 factor. But let's see how tight this is. You'll see that the column rank, given a rank, the column rank will nicely take all values in the complete spectrum. So just take the matrix 1, 0, 0, 1. Okay, so this has rank equal to 2, and the column rank would be, so everything is m equals 6 now. So the column span is all A comma B, where A can take anything, B can take anything. So it's log 36 base 6, so it's 2. On this side, just take 3, 0, 0, 3. Okay, so the rank is 2, which means that rank by log 6 base 2 is okay. So now what is the column rank? The column rank is exactly A comma B, where A is 0 or 3 and B is 0 or 3. So you have log 4 base 6. So it takes it can occupy anything here.
Yeah, but column rank it has additivity which rank didn't have. So rank has approximate additivity, but you couldn't have seen it directly. You needed to come up with.
When you mean additivity, do you mean the a plus b is less than or equal to a plus b, or this rank? Yeah, here, right. But approximately this holds because of column rank.
You don't want to lose this factor in each step of the induction.
Right.
So.
Right. And is column rank equal to row rank?
I didn't work it out, but I don't know. I mean, all you can say is it's you can again sandwich it. You can sandwich it between.
Oh, but that's also additive, but that's also additive only when the zero is in the other location.
Uh,
Right?
no, you can always back calculate. It will still be an injective map. You can always.
No, if you look at, column rank is additive when the zero is in the upper right corner, but if it's
No.
Oh, right.
Then you can define. Yeah.
You can turn upside down.
Okay. So with this in place, okay. So this fixes problem 2, and let's quickly fix problem 1.
So just a minute. So for the submatrix lemma, instead of an all constant submatrix, it would be enough to
Mod.
for a rank 1 submatrix.
Yeah, sure.
But that doesn't happen.
No. But now we'll see that. Yeah, right.
In principle, it could be a bit bigger.
The factor you're saying it might be better.
I mean, it's a weaker conclusion.
Yeah, the rank 1 you can reduce by 1 over n and get to them.
Yeah.
I mean, you can always choose the most popular column, right? Okay. So I'm running out of time. So. Okay, so before I erase this, okay, let me erase this. Okay, so what if omega is not primitive, right? Right. So I mean, here omega need not be primitive. Let's say omega has order 2. Then in order to use the submatrix lemma, you go you look at the sets A and B modulo 2, and you can do some things to ensure that modulo any factor of M there is no collision. So these will still remain sets. Once you go to mod S for any S, then omega starts becoming primitive, right? If omega has order S, if I look at set A reduced mod S and set B reduced mod S, omega is primitive now. But the problem is that the monochromaticity is mod S. It's not mod M anymore, right? Okay. So what you will get is you have P here. You will get a submatrix which is C mod S. Right. Okay. So we'll do the same analysis now. So let's say this had column rank CR. Okay. The CR of P is N. So we'll again complete this, and then you get C, and let us look at this matrix mod S. Each entry you look at it mod S, so that I don't have to write C mod S each time. Okay. Now you add a matrix which looks like minus C 0 0 0.
Let's say C was 0 on this.
Okay. Yeah, yeah. Even this has column rank at most 1. So now you have 0 here, right? Now if you use the column rank definition, then so this is A mod S, B mod S. So you know that at least one, let's say this has rank column rank CR by 2. where CR is the column rank of this matrix and not P, right? It's the column rank of P mod S. Okay, so at least column rank of in the submatrix, the column rank of A modulo one of the factors went down, right? Column rank of A did not go down. Let's say column rank A when looked at mod 2 went down. So now what we'll do is we'll do some kind of bookkeeping. So okay, so let's start with a given matching vector matrix, and let's keep track of the column ranks mod 2, column rank mod 3, and column rank of the matrix mod 6. I'm not writing, it's over Z6. Okay, so let's say you are at a stage I where this is X, Y, Z, and you can assume that all the column ranks are at most n to start with, because you can show that column rank of any matrix S is at most rank of that matrix mod S by the equivalence, and rank of any matrix mod S is at most rank of the matrix without any mod S business, and this is at most n, right? So each one of them is n to start off with. Now let's say you're at a stage I, and the column ranks at this snapshot and at this particular instant are X, Y, and Z, and you have some matching matrix Pi, and let's say this gave you an omega of order 2. Okay, so the next step, this is X by 2, okay, but these are still, in the worst case we'll assume they are fixed. Okay, so then you get something like the rank, so you get C R by log R at this stage of the matrix mod S. So times Pi, but by the equivalence of rank and column rank, you'll just lose out a constant log 6 factor and replace rank by column rank. Okay, because we had that column rank is less than equal to rank and at most R by log m, where the matrix is over Zm. So here it's over Zs. So I can replace the rank at this stage mod S by column rank mod S, which is X at this instant. So I'll write here Cx by log x, and I'll get an extra log 6 factor, which I'll hide it in C prime. Okay, so now at this stage you have such a, so Pi plus 1 is of size at least this. Okay, now this process is going on. Look at the next moment where you have a mod 2 character biased, order 2 character biased. Let's say it's at J. So here again you have a character of order 2 that is biased. So again this will go down by a factor of 2 now. So you'll get X by 4, at most X by 4. It may have gone down here as well, right? And these may have gone down, we don't care about this, but this is at most X by 4 if I get a character of order 2. Okay, so then at this stage observe that Pj plus 1 is by a similar argument 2 to the minus C prime x by 2 by log x by 2 Pj, right? The column rank mod of order, the column rank P2 went down, and the size is governed by the submatrix lemma, and the relation between Pj plus 1 and Pj is just given by the column rank mod 2. I mean, that is where we are using the submatrix lemma. So everything is dictated by that.
So just saying it differently, you want to say that if you repeat it long enough, at least in one column you'll get
Hit 1.
Yeah, you'll hit one, and this is the column you focus on now. It happens to be.
Let's see. Okay, so let's say this is the one. Yeah, so we'll continue this process until one of them hits 1, right? The column ranks. Okay, so.
There's some more honesty, right? I mean, if the rank of Z went down, then the rank of Y and A.
In this case, yeah, but when you have a general M and you'll have to keep track of all the factors of M. Some may be factors of other factors, but
No, but also there is monotonicity. So if you have someone goes down, then
all its factors, divisors would go down, yeah.
right.
But you don't lose out much because since M is constant,
No, why don't you look just at the prime factor of this guy? They will go down.
yeah, but then what if M is not a product of distinct primes?
Even if it's not a product of distinct primes, modulo the distinct primes, things will go down. If they go down by anything, then the factors will go down.
I think what is important is you didn't look at every row. So what controls the loss between from one row to
No,
the
I
next row?
understand this. I'm just saying it's not clear to me why to look at all the factors of M as opposed to all prime factors.
I'm explaining why. So what goes on in one row and the second row is some loss. Right? Because you lose is some column rank of P modulo something. And you cannot control
Now you cannot control column rank of P mod, let's say S, by column ranks of its factors for a general S. This would have worked if M were a product of distinct primes, and that is what we were doing earlier. We kept track of individual column ranks mod Pi's, and when for a given S, when all its prime factors went down by 2, then you could say that okay, the general rank R also went down by 2 because R is the max of ranks mod Pi's, right? But that does not work. That does not require column rank business, but it does not work when M is not a product of distinct primes. That is why we needed this.
So even if you look at the prime power factors, then
No, because S can be anything like P to the alpha 1 prime, P to the alpha 2 prime, where alpha 1 prime, alpha 2 prime are less than alpha 1, alpha 2, the maximum possible. And now it's kind of, yeah, you'll need to control its rank mod P1 to the alpha 1 prime and P2 to the alpha 2 prime, and then prove something like the rank of S is max of rank of P1 to the alpha 1 and rank of P2 to the alpha 2. But before trying to do, because yeah, after looking at the fact that this had rank 1, we didn't really believe anything from that point. So yeah, before that this worked out. So okay, so if you do this process and continue till some say column rank of the matrix mod 2 is 1, okay, then you stop. So by this time, how much did we lose out on the size? So each factor would have led to this kind of a geometric summation, right? You do the entire summation factor wise. So you look at each factor, it will induce some summation of the form x by 2 to the I, and there are 3 factors. So in the end, you lose out something like 2 to the minus c double prime n by log n p0. Okay, so now you have a matching vector matrix which has column rank equal to 1 when looked at mod 2 or mod any S. and it is huge in size. Okay, if P0 is much greater than C double prime. So now look at this matrix PL. Okay, so right. So if column rank mod 2 is 1, it means that the column span of P2 is at most 2, right? Because column rank is the column span log whatever it's over, right? So this cannot have more than 2 distinct columns. You take the most popular column. Okay, let's say you lose out a 1/2 factor, so you get the first few columns without loss of generality. So what did you achieve? You saw that each of these columns are identical, and since these are 0 mod 6, they will be 0 mod 2 as well. And since the columns are identical, you get that this entire matrix is the all 0 matrix, right? Okay, so what have we achieved? We lost another factor of half, and we got a matching vector whose matrix is all 0 mod 2. Now by the similar argument, it will be a matching vector mod 3, and this time we'll use the stronger polynomial bound for primes, and it cannot be more than polynomial in size, right? So if you call this P prime, then P prime corresponds to matching vector in Z3. So P prime has to be at most n squared, polynomial in n, but you have a super polynomial sized matching vector. This leads to a contradiction. And as before, this will extend easily as long as M is a product of distinct primes, because you obtain that column rank mod some factor of M is 1, which means that you get an all 0 matrix mod S, and this would mean that it's a matching vector family in Z M by S, because S and M by S would be co-prime. But if M is not a product of distinct primes, then you have to do some more work, and then you can show that if P prime is all 0 mod S dividing M, then P prime cannot exceed matching vector M by S, but with a slight increase in the rank. So instead of a matching vector in Z M by S, you'll get a matching vector in Z M by S with a higher rank. But since log M is a constant, you don't lose out much. And you can use the inductive hypothesis on M by S in the general case. But yeah, this won't work in the first theorem, because in theorem 1 we are trying to prove something like this. So here the coefficient in front of rank it's very sensitive to that, right? So you cannot just push in a log M factor there. But here you have something like n by log n, so you can do whatever you want with the thing in. So yeah, I guess. Yeah, that's it. The second theorem was not so modular and neat as the first one.
So this n over log n became something much better, then this will start saying things about this growth or these multilinear polynomials which represent n, right?
Yeah, you'll need a sub-exponential bound. If you get exp of log epsilon to the n, then you'll get a lower bound on the order of like log to the 1 by epsilon n. Instead of the current log to the 1 by Rn, you'll get omega log 1 by epsilon n. So okay, let me just write this down. So mv comma n at most exp this would imply omega log. I think you'll get a 1 epsilon minus 1 or something, but yeah. For weak representing with R.
Yeah, it's at least omega.
Oh no, above.
No, upper bounds.
Oh, if you
This is
prove
good.
that, oh, right.
This
Yeah,
is
yeah, it will,
it's saying that the rank is large enough,
Yeah, yeah, yeah.
and Goldmurch gives you a low rank construction if you assume very low degree.
but we are very far from this because, well, anyway, from
Even this is
from
with
correlations, you will never get even anything close.
to log 1 bits.
Yeah,
Okay.
so I was going to ask about this. So, I mean, everything starts from a really weak assumption, namely that there is some bias, some Fourier coefficient that is biased, the matrix is biased.
And also the rank is low. It's useful, important to look.
Yeah, the
Yeah.
rank is, yeah, we know which space we are at, but there is a bias. Now, you know much more than there is a bias. You know that there are zeros on the diagonal.
Yeah,
and,
yeah.
all the other things are not.
But we are
you
using
forget.
we are not
You're
not just
it
using
in
bias,
the-
right?
Yeah, that's right. You're using it in the
Even yeah, while combining, because the monochromatic rectangle can be just anywhere. Then you use it to get back your original matching vector matrices, go down, use inductive hypothesis.
Yeah.
But this is not using it in the
But-
strongest.
But that's where you use PFR. PFR you use
Just assuming bias and low rank.
bias, where you could use, I mean, something stronger, and you can use that every row is biased, and every
Yeah,
column is
we're
biased.
trying something like that. Like you have lots of large Fourier coefficients,
Yeah.
but if you just do the large Fourier coefficient, if you just do Parseval, you get the same m to the n by 2. Bound, then we tried some Chang's lemma, but it was very sensitive to the coefficient in front of n, so even that didn't work out, but still working on it.
So if you improve the submatrix lemma to A prime at least delta A, you get some algebra.
I mean, yeah, you'll get a geometric sum, right? If you anything in terms of rank R, if you know that if you get any bound f of R, then if this summation is bounded, you're through, right? So it's yeah. So this is like if you can